Okay, assalamu alaikum. Today we are going to talk about the analog to digital converters in microcontrollers. Basically, all the data around us in this world is analog, and when we work with digital components, we need to convert this analog values or these analog values to digital. These analog values can be voltage, can be current, can be any different sensor readings. So we want to know how do we convert analog to digital. Of course, this is not new for you, but let's go through the first part of our lecture. We are going to talk about analog to digital converters. So the first thing we are going to talk about is what is an analog to digital converters and what are the characteristics of an analog to digital converter. So assume that we have an analog signal, and this analog signal will be having on the x-axis it will be time, and on the y-axis of course we are going to have the voltage or current, and we want to convert this analog signal into digital values. In order to do that, we need to take samples at discrete times, and this is called the sampling of a signal. After we do sampling, we project the samples or the intersections of the samples to the y-axis and get our voltage value. Now the division of the y-axis is called quantization. So in the x-axis we have sampling, and on the y-axis we have the quantization. Okay. Now the analog to digital converter we are going to use is basically built inside our microcontroller. However, if we are using a microcontroller that does not have a built-in analog to digital converter, we can use either the ADC0804 successive approximator, or we can use the 8-bit flash type converter. I'm going to talk about both these two types today and see what is the difference between them, in order to understand and comprehend the idea of analog to digital converters. Now, what really happens? Let's say that I want to read the temperature, and based on this temperature I want to open a window. If the temperature is too hot inside the room, I want to open the window too wide. If it's a little bit less, open the window with respective to the temperature. So first of all, I need to read my physical value. Let's say here it is the temperature. I need to read it, and I need to convert it using a transducer and signal conditional into voltages. Now these voltages will be fed to an analog to digital converter, and this analog to digital converter will basically change the continuous value into digital. Then it will go to the microcontroller itself. It will take from the input ports, it will process and send the output to a digital to analog converter, where this digital to analog converter is controlling an actuator. This actuator of course will be either a motor, will be a stepper motor, a DC motor, depends on what type of actuators what our system is designed for. Now, two things we need to understand, which are sampling, sampling and quantization. Sampling and quantization. So we said sampling is basically taking samples on the x-axis, and quantization is on the y-axis. So what is sampling? Sampling, the analog signal is extracted usually regular space times. The samples have real values. These samples are then quantized using the quantization and then changed into digital values. So to understand this, assume that we have an analog signal. Hope my drawing will be clear. Okay, we have an analog signal, and this analog signal is something like this. Okay, on the x-axis once more it will be the time, and on the y-axis we are going to have our voltage. Now when we say sampling, we want to divide the samples based on time. Let's say we are going to divide it, these axes, we are going to divide them to give these samples. So we have here T1, here T2, here T3, and here let's say T4. Now if we want to apply, okay, if we want to find the values of the samples, we are going to draw a straight line up and see the intersection over here, then a straight line up here, a straight line up here, a straight line up here. Now as you can see here, the distance between T1 and T2 is called the sampling time, okay, sampling time, or I will call it just simply T. And we all know that F is equal to 1 over the time. Frequency is equal to 1 over the time. Now assume that we want to take these samples. Of course, after we do sampling, we have to do the quantization. In order to do the quantization, I'm going to draw the lines and see the corresponding values on the y-axis. I'm going to come to it later on. But now you can see that if I'm going to use these samples only, I'm going to end up with only 4 different values on the x-axis, on the y-axis, sorry. Now, on the other hand, what we can do is we can create more samples. Before that, if I want to create more samples, this means that T needs to decrease. So what I'm going to do is, once more, sorry for that. Now I'm going to create, here's T1, here is T2, T3, T4, T5, T6, T7, T8, T9, T10, T11, T12, and so on. So I will create more time, and as you can see over here, we once more F is equal to 1 over the time T, and since T has decreased, this means that the frequency has increased. So as we increase the sampling frequency, we will end up with what? We will end up with more samples over here. More samples means what? Means we can find a digital representation for this signal, which is quite accurate to what actually is happening. So this is sampling. As we increase the number of samples, you can see that the signal is giving us more and more. Yani, we increase the number of samples, we can duplicate this signal easily. Now, how about the y-axis? Now, when it comes to the y-axis, it depends how many number of bits are we using. What is the size of the analog to digital converter? Assume that I am using a 2-bit ADC. 2-bit ADC means what? Means 2 to the power 2, which is equal to 4 different voltage levels representing this circuit. So this means I'm going to have here V3, V2, V1, 1, 2, and V0. These are my values, or V1, V2, V3, V4, whatever. Now, what will happen is we start to draw the lines to see how these signals are represented. Just draw like this. So we can see that all our signals are just between V2 and V3. Now, assume that I increase the resolution. This is what we call the resolution. Assume that I increase the resolution. Now let's assume that I'm using a 3-bit. Okay, I just increase 1 bit, 3-bit ADC. Now if I'm using a 3-bit ADC, what will happen? I will have 2 to the power 3, which is 8, and now each one of these will be divided to one extra level. Now we have 8 different levels, and if I'm using a 4-bit, this means 2 to the power 4, which is equal to 16, and in this case we will be dividing each one of these into extra. So now you can see we have more and more levels. This will help us to reproduce our circuit in the correct way. Now, our analog to digital in the microcontroller is basically using 10 bits. 10 bits means 2 to the power 10 is 1024 different levels for a voltage range from 0 to 5 volts. Okay, this will give us around 24 millivolts per digit. Okay, I'm going to come through that in our slides, but this is the idea behind sampling and quantization. Now, again, once more, you can see here we have a sample, and the range is divided into 8 different levels, and you can see that these 8 different levels will give us a 0.26 per level, and this is our sampling period. As we increase the sampling frequency, we decrease the time between each sample and the next sample. This in turn will give us very good values. Now, the sampling theory specifies that an analog signal with a frequency of f max can be reconstructed if the sampling rate satisfies that f sampling is greater than or equal to f max, and this is what we call the Nyquist rate. This is what we call the Nyquist rate. In order to reconstruct a signal from a digital signal, an analog signal from a digital signal, the sampling of the original analog signal must be twice the frequency of a signal. So if I have an analog signal of a frequency of 1 kilohertz, my sampling rate should be at least, or my sampling frequency should be at least 2 kilohertz. This will guarantee that I can reconstruct the original 1 kilohertz afterwards in the right way. So again, if the sampling rate is fs, the maximum frequency that the signal must not exceed is 1 over half the sampling frequency. This is again the Nyquist frequency. Now, quantization and sampling. What we are going to discuss here is how we do analog to digital converters. A few things you should know. Consider an n-bit analog to digital converter. N-bit means 3, 4, 5. In our case, we have 10. Let V reference be the reference voltage, which is the maximum voltage that we can reach. Vn is the analog value that we want to convert. V minimum is the minimum value, and again, usually V minimum is basically set to 0. Then the analog to digital output is basically dn-1, dn-2 up to d0. And once more, the d is the round down of Vn, the digit Vn minus V minimum over the step size. Vn minus V minimum over the step size. This is the analog to digital output. Rounded, of course. Yani, we get an analog value. How do we get its representation in digital? We are going to get the round down of Vn minus V minimum over the step size. So what is the step size? The step size is equal to V reference minus V minimum over 2 to the power n. V reference minus V minimum over 2 to the power n. يعني if my V reference is equal to 5 volts and my minimum is equal to 0 and n is equal to 3, I will get the step size is equal to 5 minus 0 over 8.625 milli, or sorry here, volts, which is, I will go back here. This is the step size for the one that I just discussed. Okay, now here you can see a 3-bit analog to digital converter. On the first step we get 0.625, then we add until we reach 5 when we count up to 8. طبعا count up to 8 starting from 0, so it will be from 0 to 7, which is 8 counts. This is for 3 levels. For our original analog to digital signal, if we do this based on these samples and based on 3-bit quantization, we are going to find this is our output. Now you can see that this bit over here, since we are doing round down, again remember we are doing round down. Round down means we are going to choose this level over this level. This is called quantization error. This is called quantization error. Here also we have a quantization error. Here we have quantization error. Here we have quantization error. Here we have quantization error also. The quantization error, we want always to decrease this quantization error. We don't want a lot of error in our signal. The more the quantization error is lower, the better our signal is going to be. So some parameters that we need to remember when we do analog to digital is number of bits n, which is the higher the number of bits, the more precise the digital output is. So I told you earlier, if we have n is equal to, it's 2 to the power n here, n is equal to 2, we will have 4, n is equal to 4, we will have 16, n is equal to 10, we will have 1024 different levels. Quantization error is the average difference between the analog input and the quantized value. The quantization error of an ideal analog to digital converter is basically half of the step size. And again, step size is equal to V reference minus V minimum divided by 2 to the power n. The sampling time, a sampling capacitor must be charged for a duration of T sample before conversion takes place. The conversion time is the time to convert the voltage on the sampling capacitor to the output voltage. Now, in order to understand the more about the analog to digital converters, we need to talk about the flash analog to digital converter and the successive approximator analog to digital converters. These two converters, each one has its own advantages and its own disadvantages. Okay, so again, which one is better? We cannot compare apples with oranges. It depends on how much you are willing to pay for your analog to digital converter. So first one is the successive approximator. In the successive approximator, we have a priority decoder. And if you do not recall what's a priority decoder, let's talk about the decoder. The decoder will basically have 4 inputs, let's say 4 by 2, or in general, it is 2 to the power n by n. Okay, so 4 by 2 is 2 to the power 2 multiplied by 2. Now, in the 4 by 2 decoder, we are going to have the inputs as A0, A1, A2, and A3. Cannot draw lines here. Okay. Okay, our outputs is, let's say, I1 and I0, and the values once more. If we have an input of 1 0 0 0, then we are going to have the outputs as 0 0, then 0 1 0 0, then we are going to have our output as 0 1. If we are going to have 0 1 again, I think by now you remember the decoder, we discussed it many times, and at the end this is our final input, which is for A3 and giving a value of I0 I1. Now a priority encoder will have a few different things. A priority encoder will give priority for the most significant bit. So over here, if the values are don't cares, what do you mean by don't care? Don't care means if it's a 0 or a 1, it doesn't matter. The most significant bit is the most important one. The most significant bit is the most important bit. So based on this, this is my V reference. Okay, and this is my VN, and this is my priority encoder. Now this is an R to R ladder. This is an R to R ladder. Basically, in this R to R ladder, each two resistances are basically in parallel. So what is the value of the resistances? All of them, they have the same value. What is R equivalent for them? What is R equivalent for these resistors? So this resistor is connected from this side to ground, and this resistor is connected from this side to virtual ground. Okay, so these two are in parallel. R in parallel with 2R. Okay, R in parallel with 2R. R in parallel with R is half R, plus R is 2R, and so on. We get the equivalent resistance to be at the end equal to R. Okay, we get the equivalent resistance equal to R, and this is basically to do a voltage divider. So if my voltage over here is 5, and sorry, I will put it as 8. If my voltage over here is 8, then the voltage here is 7, then here it is 6, here it is 5, 4, 3, 2, 1, and here is 0, because this is a voltage divider. Okay, because this is a voltage divider, and all the resistors in the voltage dividers are in parallel, and all the resistors are having the same value. Okay, so we have this arrangement. Here we have V reference, which is equal to 8, and so on. And let's say that my Vn, okay, let's say my Vn is equal to 4. Okay, this is a comparator once more. My, sorry, let me fix it. My Vn is equal to 4 volts, and my V reference is equal to 8. So first of all, here 4 is compared with 7. Is 4 greater than 7? No. Then 4 is compared with 6. Is 4 greater than 6? No. Then 4 is compared with 5. Is 4 greater than 5? No. This is 0. Then 4 and 4. Is 4 greater than 4? No. Then, sorry, the 0 should be here, and I will delete this one. Then we have 4 compared with 3. This is 3, and this is 4. We get, I'm sorry again. Okay. So here, this is 3 volts and this is 4. Is 4 greater than 3? Yes, we get here 1. Then is 4 greater than 2? We get 1. Then is 4 greater than 1? We get 1. And the last one input is already 1. So over here you can see, using the priority decoder, we are going to get the value of C3 as our output. Advantages. This is the fastest type analog to digital converter. When we say fastest type, we are talking about speed. It takes one, this needs to be written in red, it takes 1 clock cycle. Okay, it takes 1 clock cycle to finish the conversion. The next one is basically the successive approximator. The successive approximator uses a successive approximator register. I'm going to talk about it. This successive approximator register compares between the values. So we get our input here. We give our input here, and let's say our input will be once more 4. The successive approximator starts with the numbers. If V reference, okay, if V reference is equal to 5 volts, let's say the V reference is equal to 5 volts. So the first output of the successive approximator will be 1 and all zeros, which is 1 0 0 0 0 0 0 0. So out of 5, if you want 5, you want all ones, so this will be equivalent to 2.5. Is 4 greater than 2.5? Yes, so this one will stay. Then we go for the next bit, 1 1, so it will be 0 0 0 0 0 0. So the first digit will give you 2.5, the second digit will give you 1.25, the third digit will give you 0.625, the third digit will give you 31.125, and so on. You keep dividing by 2. So every time you add, we are going to add 1.25 to this one. It will give you 3.75. Is 3.75 less than the is 4 greater than that value? Yes. So these 2 digits will stay, and so on. It will take you around 8 clock cycles to finish. But it was much more cheaper to compare to this circuit. This circuit is very expensive. I did not talk about this disadvantages. The resolution is low. It is very expensive. And it consumes high power. All of these comparators are expensive, and it's very difficult to get exact values of the resistors. So it's not practical, but it is available. If you are able to pay the money, it is available. Again, it's expensive, but it is available. Compared to the successive approximator, it is quite cheap and you can easily get it. So for instance here, if my VN was, okay, if my VN was around 3.5, first of all, I will go 2.5 plus 1.25, 3.5 plus 3.25, 3.125, okay, and so on until I get my value. So my output will be 101. Again, the successive approximator starts at each digit and goes up in that particular manner. Now I will stop here, and in the next part I'm going to talk about the analog to digital converters in the 80 mega 16 family.